Bam! Mr. Taru, and happy St. Patrick's Day. On this day, we're going to be looking at question 4 from the 2018 AP Calculus AB test, where they give us a table of information. They often give us information as opposed to just a function to work with to make sure we know all the actual calculus that's going on. And we're going to have a 4-part question here where we are going to estimate h prime of 6. We're going to estimate the slope of the tangent line at a particular moment in time. We're going to have a question that is dealing with the mean value theorem, a question that is dealing with the average value theorem, and a trapezoidal sum. And we're finally going to have our last part be a question where we're working with related rates a bit. So let's get started. In the description you're going to have a timestamp that links to the AP college website where you can find the PDF of these questions, a PDF of the marking scheme, a PDF of the scoring master grader's commentary on the test, and explains where students most commonly miss their errors, and get all kinds of good information to help you do as well as possible on this AP test. So it says here, estimate h prime of 6, and more as the years go by, they're really emphasizing this even more. Using the correct units of measure, interpret the meaning of h prime of 6 in the context of this problem. Don't just give them a number. Don't give them a number with the correct units of measure. Actually explain what it means in the context of this problem. Not only in the context, but you'll be explaining actually you understand what a derivative is actually describing. So for part A, we're going to say that h prime of 6 is approximately equal to, well, going to our table of values here, we have time measures of 2, 3, 5. We skip over 6, get to 7 and 10, and then some actual heights of this tree. So we're going to say that h prime of 6, the slope of the tangent line at the t value of 6, is approximately equal to h of 7 minus h of 5 divided by, of course, 7 minus 5. Y sub 2 minus y sub 1 over x sub 2 minus, well, x sub 1. And h of 7 is equal to 11. H of 5 is equal to 6. We're going to have that over 7 minus 5, which is 2. And we get 5 halves. Now we need to explain what that means with the correct units of measure in the context of this problem. Well, it means that derivatives are a rate of change for h prime is a rate of change for h. H being the height of the tree. So the height of the tree is increasing. Now I'm saying increasing. You can use the words of increasing and decreasing. And actually it's a little bit safer I just say it's changing, because if my slope is negative and I recognize that as a decreasing rate, then I would have to say that it's decreasing at the rate and sort of drop that negative sign. If I say it's changing by, and I use the negative value that I get from my slope, my derivative, well then I'm safe. So if you use the words of increasing and decreasing, make sure that if your slope is negative, you can't say it's decreasing by a negative rate, because that kind of like that double negative cancels out. But it is positive as increasing. I'm going to go ahead and keep it with that. The height of the tree is increasing by 5.2 what? 5.2 meters per year. So make sure again you use those correct units of measure. And if you stop there, you're not going to get full credit. Whenever you talk about the amount of change, rates of change, area, derivative, whatever, you need to be specific about the time period of which you're measuring this. And this is this tree's growth is not, I'm sure, linear over all of its life. It is at this specific time point, at or when t equals 6 years. And I'm perfectly happy with this solution. Again, if you go to the AP College Board website and you look at the marking scheme and you look at the master grader's comments on how all the students sort of like made those common errors to lose points, you'll get some more insight as to what was acceptable and not acceptable to write. But as long as you have the correct unit of measure, you have, of course, maybe a changing by or an increasing, decreasing by the correct number, and you're specific about the time period, you're probably going to be okay. Let's talk about part B coming up right now. Part B, we're going to explain why there must be at least one time t for t being on the open interval from 2 to 10 such that h prime of t is equal to 2. Now, to give myself some more room, I've erased the original wording of the problem, but it did say that h was twice differentiable. And whenever they tell you that in an FRQ on your AP test, they're basically giving you some justification as to why you can make the statement that a function is continuous. Because if a function is differentiable, it has to be continuous at a point. There cannot be a sharp bend. If a function is differentiable at a point, then it is going to be continuous throughout that entire domain. And we need that as one of our condition checks, either thinking about continuity or differentiability. Those are common condition checks for intermediate value theorem, mean value theorem, and extreme value theorem. The extreme value theorem is, and intermediate value theorems, well, they need the continuity, but for the mean value theorem, you need that differentiability as well. And then we have two mean value theorems. There's one for derivatives and there's one for integrals. Well, we're talking about a derivative right here, so we must be thinking about the only theorem that basically allows us to state that on some interval we can be guaranteed that our derivative is equal to a particular value. The mean value theorem says that as long as a function is continuous and differentiable on a closed interval, and on that closed interval you get some kind of slope of secant line, some kind of average rate of change. Well, then you're guaranteed a c somewhere on that open interval, because we've already looked at the endpoints, whereas the whereas the instantaneous rate of change, the slope of the tangent line, is equal to the slope of the average rate of change, or the secant line. And that's really where we're going with this. We need to recognize that the wording of the problem is asking us to work with the mean value theorem and then start checking all of the conditions. First of all, where do we have an average rate of change that is equal to this instantaneous rate of change which we are concerned with? 2. And this threw me for a bit of a loop. A lot of these problems that deal with mean value theorem really just kind of focus on the endpoints of a closed interval. This happens to be open, but you might look at the 2 and 10 like I did initially and go, well, the average rate of change, 15 minus 1.5 over 10 minus 2, you start working that out, it does not come out to be an average rate of change of 2. So maybe we're thinking about somewhere within the interval from 2 to 10, like 11 minus 2, which is 9, over 7 minus 3, which is 4. No, 9 divided by 4 is not equal to 2. But when you focus in on the t value of 3 and 5, we have 6 minus 2 is 4 divided by 5 minus 3, which is equal to 2. Yeah, 4 divided by 2 is equal to 2. That's where we have that average rate of change of 2. So with proper notation, we're going to say that we're checking and working with h of 5 minus h of 3 over 5 minus 3. Well, that's 6 minus 2 over 2, which is 4 over 2, which is equal to 2. Boom, we found a place using this information that we got about function h where the average rate of change is equal to 2. Well, then on that interval from 3 to 5, we need to have that continuity, and we have the differentiability stated. So h of t is continuous on the closed interval from 3 to 5 and differentiable on... Now, I'm not an AP grader. This is kind of bothering me a little bit. The scoring guideline for this says that the h of t is continuous on the closed interval from 3 to 5 and differentiable on that same closed interval. You can't take a derivative of a function at the endpoint of a closed interval. I think it's coming from the fact that originally we're given this interval from 2 to 10, being told that this is where h is twice differentiable. On this interval, not sure if this is right or wrong, but I really don't like to say because it goes against everything I've said in class, and my textbooks say that you can't take a derivative at an endpoint on a closed interval. So I'm going to say that h of t is continuous on the closed interval from 3 to 5 and differentiable on that open interval from 3 to 5 because, well, it was stated that h of t is differentiable on the open interval from 2 to 10. So we have that the average rate of change between the t value of 3 and 5 is 2, and we have our condition check for the mean value theorem that h of t is indeed continuous on that closed interval and differentiable on the open interval. So therefore, by the mean value theorem, which I'm writing out, but on the AP test you can just write MVT. So by the MVT, there is at least one C on 3 to 5 such that h prime of C is equal to 2. And that is our second example, or part B of question 4. Let's move on to part C right now. All right then, part C. Use the trapezoidal sum with 4 subintervals to approximate the average height of the tree over the time period or interval from 2 years to 10. Well, to do this problem, you have to know how to find the average value. And the average value is going to be found by doing 1 over b minus a times a definite integral from a to b of whatever your function is. In this case, it's h of t dt. So we're looking at doing, I might need to get this down because I know that the arithmetic is going to be slightly annoying here, which I'm going to try and do all the arithmetic and simplify. So you can see right down to where the final answer is. So 1 over b, which is 10, minus a, which is 2, times the definite integral from 2 to 10 of h of t dt. You always want to let the graders know and see what you're doing. And the 4 subintervals are right here. They are 1, 2, 3, 4. So they built a table for to work quite nicely with this question. Shocking, right? So we have 1 over 8 times, now we have definite integral notation, but we don't have the actual function to integrate and then plug in the values of 2 and 10. Now we're going to estimate the area off the table using a trapezoidal sum. And you know, like the function's going along and we've got a trapezoid and we're going to find the area of that trapezoid and another trapezoid, find that area, another trapezoid, find that area. So as long as we know how to find the area of a trapezoid, we are good to go. And the area of a trapezoid is 1/2 the height times base 1 plus base 2. Well, the height is the horizontal distance between the bases, and actually so it's going to be a change along the t-axis, and then the height is going to be the values that we're getting out of the table. So, and I'm going to do this as if you basically know nothing more than what the area of a trapezoid is, because maybe your teacher didn't hit the trapezoidal sum very hard because of the way it's structured in the AP test. A lot of times you just have to know that formula. So it's going to be for this trapezoid, it's going to be 1/2 the height, which is 1, times base 1 plus base 2. Well, I'm going to write that 1.5 as 3 over 2 plus 2 over 1, plus now the next interval we have 1/2 height. Now this height, the space between these t values is 2, and we have base 1, which is 2, plus base 2, which is 6, plus another 1/2 a height, which this time again is equal to 2. And now our heights, this is the height of the trapezoid, and the bases are going to be the 6 and the 11. And then plus one more, 1/2. Height is 3, because that's the distance between these t values, the movement along the t-axis. And we're running out of room here, but our heights are going to be 11 plus 15. Now, each of these terms have a common factor of 1/2. So I'm going to go ahead and bring that out and say this is 1/16. And that is equal to, or getting multiplied to, well, this is going to get multiplied by 2. So we've got 3 plus 4, which is 7 over 2. Plus, now we've got 8 times 2 is 16 over 1, because the 1/2 is out here. We've got 2 times 17, which is 34. And we've got 26 times 3, which is going to be, what, 60 and 18, or 78. Just going to double check here. Okay. Now, all of these have common factors of, well, we're going to make a common factor of 2. So now we're looking at 1/16 times 7 over 2 plus 32 over 2 plus 68 over 2 plus, what is it going to be, 140 and 16, so 156 over 2. Starting to slow down here, make sure I don't make a mistake. So the 2's are going to come out, well, we're going to add this first. We have 1/16. Now we have 156. Let's do this. 150 and 60 is 210. Now it's 240. Now it's 247. 249. 249 and 8 is 257. 257 and 6 is 263. Hopefully, if I did my math right. Oh my gosh, yes I did. Over 2, I'm a math teacher, but you know, hey, I make mistakes. So that's going to come out to be 263 over 32 meters. And look at the marking scheme here. Yes. It does ask for an approximation, but it's always a good idea to write this in context of the problem. So the tree has an average height of 263 over 32 meters. Don't stop, because hey, the tree is constantly growing. If I pick 2 different time periods, the average height is going to be different. So between t being 2 and 10, and now you have your specific time period that goes along with this specific average height. We got part C, part 3 coming up right now. That was part C. We have part D coming up right now. Part D. All the information's gone because we have basically our brand new standalone problem. So when you're doing your AP test, if you get stuck on A or B or C, hey, you might have another part that you can still figure out. So the height of the tree in meters can also be modeled by, now we're actually giving us a function, 100x over 1 plus x, where x is the diameter of the base of the tree in meters. So our independent variable has gone from time to the diameter of the base of the tree. When the tree is 50 meters tall, the diameter of the base is increasing at 0.03 meters per year. What is the rate of change of the height with respect to time in meters per year at the time the tree is 50 meters tall? Okay, a couple of things to catch in this that is important. What's the rate of change of the height with respect to time? With respect to time. See, g of x has an independent variable which is not time, like in years, but is in meters. You need to catch that change, otherwise you're not going to get hardly any points for this problem, even if you feel like you completely comprehend what's going on. When the tree is 50 meters tall, we have a rate of change for the base of the diameter, and x is the length of that diameter. So we have some change in x, which is equal to 0.03 meters. And again, it's in per year, per time, not per meters, which is how the diameter, x is the diameter, which is measured in meters. And at the time, the tree is 50 meters tall. Okay, well, I like to just kind of like find the derivative and start just basically saying, hey, what are you asking for? And I'm going to go find it for you. So we have g of x, which is equal to 100x over 1 plus x. Sorry for the sound of the air conditioner, but I'm in Florida and it's just necessary. G prime of x. Now here's where you got to be really careful. This is a bit of a doozy question here. With what is the rate of change of the height? This is the height. With respect to time, not in respect to the length or measurement of the diameter, which is in meters. So we're not taking the derivative of this function with respect to x. We're taking, ultimately, we need the derivative with respect to t. So think about like the chain rule. We're going to we're going to take the derivative of the outside function using the quotient rule, and then finish up with the chain rule, finish up by finishing up with the d of x dt. We're going to take the derivative of this function, take the derivative of the outside function, but then we're going to finish up by taking the derivative of the inside function with respect to t. We do this with implicit differentiation, where we had y in terms of x, but we were taking maybe the derivative of y and the derivative of the right-hand side, which had all those terms of x with respect to t. So there was always that chain rule application. So we have g prime of t is equal to the derivative with respect to x of this function. So we're looking at the quotient rule, so low d high. So we have 1 plus x times 100 minus high d low all over low low. And this would be our answer for g prime of x if we were taking a derivative with respect to x, but we're taking that derivative with respect to t, so we need to finish that up with the chain rule, finding the dx dt. And just to make sure, because sometimes I write stuff silly, good. Okay. Working with this now, we have two terms, both of which have a common factor of 100, so we're going to go ahead and factor that out. So taking a factor of 100 out of here, taking a factor of 100 out of here, we have, oh, and this is cleaned up quite nice. We have a x minus x, which is equal to 0, so we have that g prime of x is equal to 100 over 1 plus x squared dx dt. So what do we need to basically find the answer to this question? Oh, by the way, erase that equal sign, because it's a really bad idea to write equal sign next to each line of scratch work. If you miscopied something, dropped some kind of notation, or didn't have a +2 when it should have been there, and you added it into the next line, they'll have to stop grading on the AP test and give you a linking error and stop grading. It's always best to show your work without Make it logical, make it sequential, make it easy to grade, but don't put an equal sign next to everything. And then when you're done and you're happy with your final answer, go ahead and rewrite that statement that g prime of x is equal to this. We need to know what x is, and we need to know what dx dt is. Well, when the tree is 50 meters, we don't know when the tree is 50 meters tall. So I got to do a little bit of scratch work here and say, okay, what is x when the tree is 50 meters tall? I need that x to plug in here. And we've got 50 is equal to 100x over 1 plus x. Now we have 50 plus 50x is equal to 100x. That's going to give us 50 is equal to 50x, and therefore x is equal to 1. Okay, good. So with that little bit of scratch work, I found that when basically x is equal 1, when the diameter of the base of the tree is 1 meter, then the height of that tree is 50 meters. Well, when we have the base is increasing at 0.03 meters per year, there's that time period coming in, matching that proper notation. So we're basically looking at g prime of 1 is equal to, when the base of the tree has a diameter of 1 meter, its height is 50. That's equal to 100 over 1 plus 1 squared, which is going to be, of course, 2 squared, which is 4. Now, I'm not going to put in this 0.03 meters per year. I want to be able to simplify that. That's the tenths, that's the hundredths, so that's 3 over 100. The hundreds cancel out, and we have g prime of 1 is equal to 3/4. Now, I'm going to go ahead and verbally summarize this, but I'll write the statement as we call off, because this is the last part of this question, number 4 on the 2018 AP Calculus AP test. But the interpretation of this is what? What is the rate of change of the height? So the height of the tree is increasing by 3/4 of a meter per year when the tree is 50 meters tall. I'm Mr. True. Bam! Go get a 5 on that AP test.